Hi, everyone. Today I'm going to talk about list agreement expansion from Coboundary Expansion. My name is Roy, and this is a joint work with Tali Kaufman. The talk will be structured in the following way. I'm first going to present high-dimensional expanders, which are the structures in which we do agreement and list agreement testing. We're then going to see that list agreement requires some additional structure in the form of Coboundary expansion, which I'm also going to present. I will then present our results and finally give some high-level description of our method. So as I said, let's start by considering high-dimensional expanders and the connection between high-dimensional expansion and agreement testing. High-dimensional expanders are high-dimensional analogs of expander graphs. The objects that expand in high dimension are called simplicial complexes, and they generalize graphs into high dimensions by having high-dimensional structures in them. So while graphs consist of vertices and edges, simplicial complexes consist of triangles, pyramids, and so on, which are required to be closed downwards, meaning that if a triangle exists, then all of the edges that make it exist, and so on. We call all of these structures the faces of the simplicial complex, and we think of them as having a dimension. Specifically, the dimension of a face would be its cardinality -1, meaning that a pyramid would be a 3-dimensional face, a triangle a 2-dimensional face, an edge a 1-dimensional face, and so on. The dimension of the simplicial complex is just the dimension of the maximal face in it, and we call the simplicial complex pure if its maximal faces are of the same dimension or of the same cardinality. We think of pure simplicial complexes as weighted objects in the sense that the faces of every dimension have a probability distribution associated with them, and the probability distribution of lower dimensions is determined by the probability distribution of high dimensions. Another structure of interest within simplicial complexes are links of faces. Links can be thought of as the faces that a certain face can see. So for example, if we consider this simplicial complex and this face, then its link is going to be this graph, which essentially consists of all the edges it can see through triangles. Formally, the link of a face is all of the faces that contain it, while excluding the face itself. We are now ready to talk about agreement testing, and the object we're going to test are assignments. An assignment to the k-faces of a simplicial complex is a collection of functions, one for each k-face, that assigns each one of its vertices with either 0 or 1. So for example, if we consider this simplicial complex, an assignment to the two faces of it could be, for example, this assignment. We call an assignment agreeing if it agrees with some global function. So for example, this assignment is not agreeing because v2 is assigned 0 by this face and 1 by this face. We could, and for example, if we wanted to change that assignment to be agreeing, we could change v2 and have an assignment that agrees with this global function. So now that we defined an agreeing assignment, we can move on to define an agreement tester. An agreement tester is a randomized algorithm that gets some oracle access to an assignment. It then queries the assignment on two faces, meaning that it looks at the values that those faces assign to the vertices and accepts or rejects it such that the following two conditions hold. If the assignment is agreeing, then the tester always accepts. And if the tester rejects with some probability epsilon, then we can change at most a times epsilon faces to get an agreeing assignment, meaning that we change the values that those faces assign to their vertices. One simple agreement test that you can think of is essentially picking two faces that intersect each other and check whether they agree on their intersection. In 2017, Diner and Kaufman defined agreement expanders as simplicial complexes in which the simple test I presented in the previous slide is an agreement test. They also showed that many complexes exhibit this agreement expansion. They also defined one-up agreement expansion as expansion in the case where the intersection is of size k. The intersection between two k-dimensional faces are of size k, which means that they intersect on all but one of their vertices. So now that we discussed agreement testing, let's move on to discuss list agreement and list agreement testing. Our basic object of study is going to be an L assignment, which is very similar to a regular assignment, except in an L assignment, every face is given L different assignments. And we call those assignments agreeing if there are L global functions such that in every face, every assignment agrees with one of the global functions. So, for example, if we consider this simplicial complex with these two vertices, and we consider this L assignment, so as you can see, or actually this two assignments, so as you can see, this face is given these two assignments, and this face is given these two assignments, then these assignments are agreeing, and they agree with these two global functions, as these two assignments agree with this global function, and these two assignments agree with this global function. We're interested in list agreement testing. A list agreement tester is a randomized algorithm that is given an oracle access to some L assignment F. It then queries it on Q local assignments and accepts or rejects, such that if the L assignment is agreeing, then the test always accepts. And if the test rejects with some probability epsilon, then one could change at most a constant times epsilon of the local assignments and get an agreeing L assignment. It is important to stress that in this model, we think of the queries and the changes as happening to one of the local assignments of each face, and not the entire collection of global assignments. Initially, it might seem like agreement testing and list agreement testing require essentially the same tools. For example, if in agreement testing we pick two high-dimensional faces and check whether their assignments agree on their intersection, then in list agreement testing, we could pick two high-dimensional faces and check whether there exists a permutation under which the local assignments agree on their intersection. This, however, is not the case. Consider a cycle of odd length with these two assignments on its edges. And note that for every vertex, there is a permutation under which this L assignment agrees. For example, for gamma 0, this assignment agrees with this assignment, and this assignment agrees with this assignment. However, the two assignment can be interpreted as saying that the two sides of the edge are colored in different colors. And since this cycle is of odd length, it is clear that the assignment is not agreeing. We therefore conclude that we need some additional structure in order to test for list agreement. This additional structure is going to be Coboundary expansion, which we will present next. And Coboundary expansion is by considering the connection between covering spaces and near covering spaces. So let me first define a covering space. So given a simplicial complex, a covering space is a different simplicial complex equipped with a projection map that maps every face to a face of the same dimension, such that the pre-image of every face is a set of size L. For example, the pre-image of V1 would be these two vertices in this covering space and these two vertices in this covering space. And every face cannot, in a sense, distinguish between whether it is in the original complex or in the covering space. So, for example, V1 sees a triangle that contains V0 and V2, and a triangle that contains V5 and V3. And so it would see essentially the same triangles in the covering spaces. Of particular interest to us are trivial covering spaces, which are the covering spaces that are consisted of just L copies of the original complex. The second object of interest are near covers. Near covers are essentially covers, except that they only care about vertices and edges. So even though take for example this near cover. In this near cover, you can't fill in the triangles. So V0 won't see a triangle that is consisted of V1 and V2, but rather it would see a copy of V1 and a copy of V2. And much like the case of proper covers, we also care about the trivial near cover, which is just L copies of the original complex. We will define one-dimensional Coboundary expanders as complexes on which the triangle test is a good tester for whether a near cover is trivial or not. The triangle test is a test that picks a triangle at random and look at its images and determines whether it is consisted of like L distinct triangles or not by simply picking a starting point and walking along the edges for 3 steps and checking whether the walk returns to the original vertex. So for example, if we take this complex, this one is not a trivial near cover. So if we started, say, from this vertex and walk the 3 steps, we won't return to the same vertex. While if we consider this complex, which is a trivial near cover, running the triangle test would yield the same vertex, and thus the test would accept. As I said, we're going to define a one-dimensional C coboundary expander over the symmetric group with L elements to be any simplicial complex on which the triangle test is a good test for whether a near cover is trivial, meaning that a near cover passes the triangle test with probability 1 if and only if it is trivial. And if the test rejects a near cover with probability epsilon, then one can change at most the covering of at most C times epsilon of the edges in order to get a trivial near cover. It is important to note that this is by no means the standard definition of Coboundary expansion, but rather an equivalent definition for the first dimension that stems directly from a work by Sharansky and a work by Diner and Mishulam. We show that any simplicial complex that has sufficient expansion properties, specifically Coboundary expansion over the symmetric group with L elements in every link and one-up agreement expansion, supports list agreement testing using 3L queries under some small distance assumptions on the local assignments. Specifically, those local distance assumptions are that any 2 assignments to the same face differ on at least 2 vertices. We know that this limitation is inherent, meaning that without this assumption, no test can be found, and that there are non-trivial simplicial complexes to which this result holds, for example, the spherical buildings. I'm going to spend the rest of this talk by giving a high-level description of our methods. And specifically, I'm going to limit myself to the case where every 2 K faces that intersect each other on K vertices have some permutation under which their local assignments agree with each other. In order to analyze this case, we define a complex which we term the representation complex, which in effect represents the agreement test. Its vertices or 0 faces are going to be the K faces of the original complex. Its edges are going to contain pairs of faces that are chosen by the agreement test, or in our specific case, 2 K faces that intersect each other on K vertices. And the weight we're going to have put on the edges is the probability that the agreement test picks those 2 faces. And higher dimensional faces would be defined so that these would be the weights. We managed to prove that if the original complex is a Coboundary expander, then the link and all of its links are Coboundary expanders, then the coboundaries of the representation complex are testable. Before I move on to discuss how the representation complex helps us with achieving list agreement testing, let's first consider regular agreement testing from the point of view of the representation complex. So a regular agreement tester picks 2 high-dimensional faces, say the red face and the orange face, and then checks whether the assignments given to those 2 high-dimensional faces agree with each other on the intersection. This corresponds directly to picking an edge in the representation complex, specifically the edge between the red vertex and the orange vertex that, again, correspond to those 2 high-dimensional faces, and check whether those the assignments to those high-dimensional faces agree on the intersection between them. Consider an edge in the representation complex. The vertices that make up this edge are associated with K-dimensional faces in the original complex, and thus have an assignment associated with them, which we're going to draw as a vertex above that original vertex. So we're going to think of the blue vertices as the original vertices with a specific assignment, and the original vertices is just the structure. In the list agreement case, we're going to have several of those. So, for example, this vertex would represent tau with F1, this vertex would represent tau with F2, and so on and so on. Because we assumed local agreement under some permutation, and because we assumed some local distance, we can connect those vertices such that 2 of these vertices are connected if and only if they agree on the intersection between sigma and tau. This creates a near cover for the representation complex, which we're going to use in order to untangle the agreement structure. Before we show how to use the near cover in order to untangle the agreement structure of the list agreement, let's consider the optimistic case in which we already have a trivial near cover. In that case, we have essentially L copies of the original complex, each equipped with some assignment associated to it that fully agrees, because we hadn't changed any edge and those edges agreed in the first case. We can therefore use the agreement expansion in order to create essentially L different global functions for the original complex. In this case, the near cover might not be well structured. For example, the near cover that covers this triangle, in a sense, tangles two of the copies of the representation complex by having this cycle of length 6, which essentially belongs to two copies of the representation complex. Another example is if you cast back to the odd cycle example, the near cover that is associated with that 2 assignment over there would be a cycle of length 10, and not 2 copies of the cycle of length 5. Therefore, our first step in tackling the general case would be correcting the near cover into being trivial by changing some of its edges. In order to do that, we utilize the fact the original complex and all of its links are Coboundary expanders in order to claim that in the representation complex, we can bound the number of edges we have to change in order to get a trivial near cover using the number of bed triangles, which here we take bed triangles to mean triangles that are not covered by L distinct triangles. Consider now the corrected near cover of the representation complex. This is a structure that consists of L copies of the representation complex. In each one of those copies, every one of the vertices of the representation complex has a single assignment associated with it. We can therefore think of each one of those copies as running the agreement test over the original complex, given a single assignment associated with each k-dimensional face, specifically the assignment that's associated with the vertex that represents it. We would therefore try to bound the distance of each one of those copies from agreeing using the rejection probability of the agreement test. In order to bound the rejection probability of the agreement test, we're going to note the following thing. Edges that were not changed during the correction process still represent agreement, as they started from representing agreement. Therefore, the only edges that could cause rejection in the agreement test are edges that were changed during the correction process. And because we have a bound in the number of edges that were changed during the correction process, we have a bound of the distance of the L assignment from being agreeing. And we can therefore derive the distance from having L global functions. Thank you for your attention.